So let's review heat of combustion. That was something in chapter 17. So let's say we have this equation CH4 plus O2 goes to CO2 plus H2O. And let's say that we also know that we're told that this equation is exothermic, meaning it releases heat. So we know that delta H is, let's say, negative 800 kilojoules. Okay. So remember, if delta H is heat, it can same as heat. We're losing negative 800 kilojoules. So remember, if you're losing heat, heat would be on the product side. So if we added in heat, heat would actually be right here on the product side. Okay? And so those thermochemical equations are when you have an equation and then you have heat added. So heat goes on the product side if it's exothermic. If it were endothermic, it requires heat. So heat would go on the reactant side if it were endothermic. One thing to keep in mind for this test, just make sure all the equations you work with are balanced. Don't assume that they're balanced. So with one carbon and one carbon, 4 hydrogens, only 2 hydrogens. So we need a 2 here. And then we have 2 oxygens on this side. We have 2 oxygens here and 2 more here. So 4 oxygens on the right, only 2 on the left. So we'll need a 2 here. So just double check that any equation you work with is balanced, because that's going to be very important. Okay, so for heat of combustion, we're taking something and we're burning it. We're adding oxygen to produce carbon dioxide and water. And for every 1 mole, because there's a 1 in front of here, for every 1 mole of methane, we should be able to produce negative 800 kilojoules of energy. But let's say, as an example, we have 32 grams of methane. And the question is, how much heat can we produce? Okay, so what we want to figure out, it's almost like a recipe. If we have 1 cup of methane, we can make 800 cookies. You can think of it that way. But we want to figure out how many cups or how many moles of methane do we actually have. We have 32 grams, but this equation is in terms of moles. So we first have to convert this into moles to figure out how many moles do we actually have. So we add up the weight of carbon and 4 hydrogens, so that should be 16 for the weight for 1 mole. So then when we divide those 32 divided by 16 is 2. So in fact, if we have 32 grams of methane, we actually have 2 moles of methane. We have double what we actually need. So if 1 mole of methane can produce negative 800 joules of energy, 2 moles of methane, so we can actually do it like this. So we said 1 mole of methane, and again, we got that 1 from the coefficient in front. If this was a 2 in front of this equation for methane, we would put a 2 here, but we have 1 mole of methane in our equation, so 1 mole of methane here can produce 800 or negative 800 kilojoules of energy. So we would just need to multiply those together. So if we have 2 moles, we should be able to make double. Our delta H should be negative 1,600 kilojoules. We have double the amount. So same thing is true if you didn't have a full mole. Let's say this was 8 grams instead of 32. That's only a half a mole, so you'd only be able to make half as much, only negative 400. So for these problems, they'll have to give you the equation, just make sure it's balanced. They'll have to give you the delta H, or the heat that's either gained or released. Your job is to figure out how many grams, or the grams that they give you, your job is to figure out how many moles is it. So if this equation is in terms of 1 mole, if you don't have 1 mole, you're not going to be able to produce all of this energy. But if you have more than a mole, you'll be able to produce more energy. So just convert it into moles and take that mole number and multiply it by whatever heat they give you. Okay? So we'll move along to 17.3 and 17.4. So 17.3 is going to deal with our phase changes. So there's a couple things that we want to keep in mind. Remember we talked about things being endothermic versus exothermic. Okay, endo, if you think of endo and inside, energy is going inside. They're absorbing energy. Exo, if you think of exiting, energy is being released. Okay, And so there are some phase changes that are endothermic, require energy, and there are some phase changes that release energy. So to be clear, let's go over those phase changes quickly. So melting is an endothermic process. It has to absorb heat to melt. Vaporization is also an endothermic process. The liquid has to absorb energy to turn into a gas. And sublimation is also an endothermic process. That solid has to absorb enough energy to all of a sudden turn into a gas. Now, exothermic processes would be freezing. We're going from a liquid to a solid. Condensation, when we're cooling a gas off to go into a liquid. And deposition, where we're going from a gas back to a solid. So if you notice, these are all opposites. Melting is endothermic, but freezing is exothermic. Vaporization is endothermic, but the opposite process, condensation, is exothermic. Sublimation is endothermic, but deposition is exothermic. So one thing that is going to be important to keep in mind is that, let's say as an example, and I'm going to make these numbers up just so it makes a little more sense. Let's say for a reaction, the reaction required 400 joules of energy to melt. Well, if it needs to freeze, it has to lose that exact same amount. So if it requires 400 joules to melt, it's going to release negative 400 joules when it freezes. Okay, so if this is positive 400, then it's going to release negative. Let me just write this so it's a little easier to see. Okay, likewise, let's say that something requires 1,000 joules to vaporize, to turn into a gas. It's going to need to release that same amount to turn into a liquid. Okay, and likewise, let's say if something requires 5,000 joules to sublime, it's going to release 5,000 joules when it goes the other way, when it does deposition. So there's one important thing in chemistry called the law of conservation of energy, which says energy is never created or destroyed. So if it has to absorb this amount of energy to do the phase change, it has to release that exact same amount to go backwards. So that's one thing to keep in mind. So in a test, if they would give you something like, if they say delta H of fusion equals 200 joules. Okay, fusion is a fancy word for melting. So if we know that delta H of fusion is 200, well, what would delta H of freezing be? Because melting and freezing are opposite. So if it needs this much amount of energy to melt, then it would need the delta H of freezing would be negative 200 joules. Okay, so they're always opposites. If you know how much you need to do the endothermic process, it would be the opposite to go the other way. Okay. All right, so one other thing that we should review are the phase diagrams. Or sorry, the energy diagram. All right, so let's say this is 100. Let's say these are our reactants, and these are our products. Okay, so remember these energy diagrams. Okay, this is the energy diagram. So let's talk about what this means. So we start out with our reactants at 100 joules, but our products end at 400 joules. So they changed energy. So how much energy did they change? We can figure out this way. We started about here, and we ended all the way up here. So that difference in energy, that's what delta H is. That's the heat or the energy. So this one actually went from 100 to 400. It gained 300 joules of energy. So this would be endothermic. Okay, because it's gaining energy. So let's label some more kind of parts here. This hill, if you imagine, these are where the reactants started. They have to climb this big hill before they can actually get on the other side and have the products. So we have to look at something called activation energy. So activation energy is from where the reactants start to the top of that hill. So this is activation energy, and for whatever reason they label it EA, but it's activation energy, and it's the energy needed to start a reaction. So that's the activation energy going this way, but what would it be if we go backwards? So the forward reaction would be if we go from reactants to products. The backwards reaction would be if we go back this way. So if we start with products and go backwards to reactants. So if it's, let me throw in some numbers here. Say this is 600. So the activation energy, we started at 100, but we got to get all the way to 600 for the reaction to take place. So that activation energy of the forward reaction, so if we're going that way, would be 500. We got to go from 100 to 600. So that's how much energy we have to absorb before we can make the products. But let's look at it going the other way. Let's assume that we're starting with the products and we're going backwards to the reactants. So I'm going to erase this. The change would still be the same. The only difference is if it was positive going this way, it's going to be negative if we go this way. So if we're starting at 400 and we drop to 100, we lost 300 joules of energy. So one thing to keep in mind, if a reaction is positive going that way, it's going to be negative when you go back, and vice versa. If it's negative going this way, it's going to be positive going the other way. So if we're starting here for the products, we just have to do this little tiny climb to go down. We don't have as big of a steep climb as we did going the other way. But if we're going from products to reactants, we just have this little tiny climb here that we have to do. So this is our activation energy here. And that's only going to be 200. We're starting at 400. We just got to get to 600 to go and finish the reaction. So the question could be, which way do you think the reaction will go? Do you think it will go reactants to products, going that way, or do you think it will go products to reactants, going the other way? Well, we said the activation energy, if we're going this way, we're starting at 100, we're ending at 600, we would need 500 joules of energy to go that way. But if we're going products to reactants, we only need a little bit. We only need 200. So more than likely, this reaction would probably prefer to be exothermic. It would prefer to go from products to reactants. It takes less energy that way. But they could ask a lot of questions with these phase diagrams. So just to kind of summarize, activation energy is the energy needed to go from reactants to products. Or sorry, to go from reactants to the top of the hill is your activation energy. But we can also figure out activation energy for the reverse reaction, and that would just be the energy needed to go from the products to the top of the hill. Whichever activation energy is less, that will let you know which way the reaction more than likely prefers to go. So even though we drew this to be endothermic, the reaction would probably prefer to be exothermic. It's easier for it to just go this way because it takes fewer energy to get to the top. Okay? And generally reactions prefer to be exothermic. They prefer to lose energy instead of having to gain energy. Because one of the issues with gaining energy is you got to wait to get the energy from someone. But if you already have the energy, it's easy to lose it. So things prefer to just be exothermic. Another way that I think of it is it's always easier to spend money or lose it than it is to save it. So that might be a little bit easier. But reactions tend to, if they can, they tend to want to be exothermic. Okay, so let's look at a couple other things for this energy diagram. This point all the way at the top, that has a name. That's called the activated complex. Okay. And let's talk about what a catalyst does. So a catalyst can be heat, a catalyst can be an actual compound or enzyme, but what does a catalyst do? So a catalyst actually comes in, it's going to make the reaction go faster, and the way that it does that is it comes in and it lowers the amount of energy that you need to start the reaction. It's not going to get rid of it completely, but it would come in and it would lower it. So you don't have to work as hard to get it all the way up to the top. You just might have to work a little just to get to here. So the catalyst just lowers the rate of reaction by decreasing your activation energy. Okay, so this would be what a catalyst does. It lowers it. Okay, so a catalyst lowers activation energy. so the reaction takes place faster. You don't have to spend as much time trying to get the energy you need to just start. Okay. The other thing to keep in mind is you might ask, well, why do we have this big hill? Why can't we just go right straight from reactants to products and just draw a straight line that way? Well, one of the things that happens for any reaction to take place. So in order for a reaction to happen, there are two important things that have to happen. One, the reactants have to hit each other. So the reactants have to collide. So reactants must collide, which kind of makes sense. You can't cause something to change if they don't interact with each other or hit each other. So you need the reactants to collide, and you also need the reactants to collide with enough energy. So they must have enough energy. So they must have enough energy, and they have to hit each other in the right way. So hit in the right spot. Okay, we usually say hit in the right orientation. So not only do they have to hit each other, they have to hit each other hard enough and in the right spot for the reaction to change. Okay, so there is a picture. Let me see if I can find it. In your textbook, I would recommend looking at. They may help better understand how reactions take place. So it is on page 543 in 18.1. But it shows how reactants have to interact with each other. So they spend a lot of time over here trying to hit each other. So they might bounce into each other, but not hard enough. Or they may hit each other, but not in the right spot. So there's a lot of kind of trial and error of them trying to bounce and hit each other, and it takes time. And so they have to get enough energy. The more they try to hit each other, the more energy they get. So they have to finally get enough energy so that when they hit each other, bam, the reaction can actually happen. So there's a lot of waiting that actually goes along while they're trying to hit each other because these two things have to happen. And this is what we call the collision theory. So this is the collision theory. And the collision theory is just that in order for a reaction to happen, the particles must collide with enough energy and at the right spot. And so because that's not something that easily happens, it takes time. And for some reactions, it takes a lot of time. For other reactions, it doesn't take as much time. It just depends. Okay, but those two things have to happen in order for a reaction to take place. The activated complex is where we're like halfway there. So at the activated complex, the mixture is not really reactant because they've changed a little bit, and it's not really products yet because we haven't made them. So they're kind of somewhere in between, like the intermediate or the middle part would be right here at the top. And so I would suggest looking at that figure on page 543 to get a better visual because it kind of shows visually what's happening along this curve. Okay? All right. So, let's continue with 17.4. So 17.4 is Hess's law, and it deals with you may see it like this. Delta H with a little 0, or they may do it like this with a triangle H and say R. Either way, this is the heat of reaction, or enthalpy of reaction. All it is the amount of heat that may have been gained or absorbed for a reaction. But let me write out a practice problem, and I'll explain what we're doing here. So Hess's law. Hess's law deals with trying to figure out the heat. So Hess's law says if you don't know what the heat or the enthalpy is of a reaction, so if you don't know whether the reaction has gained or lost heat, Hess says just look at the steps, and you can figure it out that way. So we'll look at the steps and figure it out. But what we're trying to find is the heat of reaction. So as an example, let's say we have this reaction, 2Al plus Fe2O3 goes to 2Fe plus Al2O3. Okay, so that's the reaction. This is the final reaction we want to get to. So this is kind of our end goal. This is what we want to end up with. So for a question like this, they would have to give you the final equation, and what we're going to look at is we're going to look at the steps. So they're going to show us the steps that they took, and it's up to us to figure out how we can combine the two steps together to get to that final equation at the top. Okay, and so the other thing they also give us for the steps is they give us the heat that was needed for each step. So this is negative 669.8, and this one is negative 824.2. Okay, so we have the steps and we have the heat. Now it's up to us to figure out how we might need to use these steps. We may need to flip them, we may need to multiply, but our end goal, we want to end up with this exact equation. So the one thing I would recommend doing first is to look at the positions of things. So in our final equation, we need aluminum to be on the left. It's already on the left. So that is actually okay. So this step is, so what we're trying to do, this is like puzzle pieces. We're trying to fit the puzzle pieces together to get them to turn into this reaction. So we have two aluminums. They're right now, the aluminum is on the left of our step. It's on the left of our equation. So that is in the right spot. That's fine. So that one's fine. It's in the right spot. Okay, now next, let's look at the Fe2O3. We need it to end up on the left side of the arrow, but in the step, we have it on the right side, so they're not matched up. So what we're going to need to do, we're going to need to get this on the other side, and the way that we do that is we have to flip. We have to flip that equation. Now, whatever we do to the equation, we have to do to the heat also. So if we flip something, that means we need to change this from a negative to a positive. You change the sign. So when you flip, you change the sign. If it were negative, the energy becomes positive. If the energy were positive, it becomes negative. It was negative to start, so we're going to turn it into positive. And I'm going to flip this whole equation. So I'm going to erase it and rewrite it. But we're going to flip it. And when we flip it, what that means is what was the products now become the reactants. So this is going to turn into, the iron oxide is now going to be on this side. And then the iron would be here. To Fe plus 3/2 oxygen. Okay, so we flipped it and then we changed the heat with it. So now the heat's positive. So now this guy and this guy, they're on the left side, which is exactly what we want. So those are fine. Okay, so moving along. In our final equation, we need iron to be on the right. We actually have it on the right of the arrow. So that's also fine. Okay. And then aluminum, we need it on the right. We already have it on the right. So that's fine also. So we've already accounted for kind of everything in our final equation. So once we've done that, we don't need to change this top step. We don't need to change this bottom step. The only thing that we have to do at this point is to add the two equations together. So I'm going to add them together. So we have 2 aluminum. So anything that's on the left of the arrow, I'm going to put on the left of the arrow here. So we have 2 aluminums, 3/2 oxygen, Fe2O3 goes to, so that was everything on the left, goes to 2 Fe plus Al2O3 plus, I'll dump it down here, 3/2 oxygen. Okay, so one thing that we'll notice, a lot of things are going to be able to cancel. So 3/2 oxygen, this is the same on this side as it is on this side, so we can cross them out. And that's actually it. So that's the only thing that crosses out. So we're left with 2Al, which is what we wanted, plus Fe2O3, which is what we have here, goes to 2Fe, which is exactly what we needed, plus Al2O3. Now the last thing we have to do, because we added those equations together, we add the delta H's together. So we would take the delta H from that. We did not change that step, so that number stayed the same. And we would add it to the 800 24.2. Okay, and whatever that is, that would be your final answer, and that's giving you the heat of that reaction. So just to recap, for Hess's law, you're going to get a final equation, you're going to get steps. Your job is to figure out how the steps fit together. So you may need to reverse steps, you may need to multiply. So let's say as an example that we needed 4 aluminums. Let's say that this wasn't a 2. Let's say this was a 4. Once we figured out the aluminum was on the correct side, it was on the left side and we needed it on the left side, we would also have needed these numbers to match. So if this was 4 and this was 2, we would have had to multiply the whole equation by 2, and we would have also had to multiply the heat by 2. So you do have the ability, if the numbers don't match up in the front, to multiply or divide by numbers. But whatever you do to the step, you have to also do to the delta H. Okay? So remember, if we flip something, if we flip a step, we change the delta H to the opposite. So if it was negative, it becomes positive. But you'll be given the final equation, you'll be given each of the steps, and you'll be given the heats to go with each of the steps. Your job is to figure out how the steps can combine together to get you to the final equation. And that's what Hess says. If you don't know the final heat, just look at the heats of the steps, and that will help you figure it out. Okay. All right, just a few more points. So for 18.1 is all about how we can increase reaction rates. And a reaction rate is just how much product we can make over time. So reaction rates is for all of section 18.1. So I would suggest reading over 18.1. It's not a very long section, maybe 2 or 3 pages, but it's important to kind of get that vocabulary down. We'll just kind of go over the basics here. So reaction rates are basically how quickly products or reactants are made. So let's say we have sugar and we are adding it to water. And we want that reaction of making sugar water to happen really quickly. Okay, so there's a couple ways that we can increase we can increase reaction rates. This is similar to that solubility section you guys did. So some of the things that we'll talk about how you can get things to dissolve is very similar to how we can get things to react. Okay, so one thing we can do, let's say we wanted the sugar to react more in the mixture, or we wanted it to react quicker, we could increase the temperature. And what that's doing is when we increase the temperature, we're giving those particles more energy. So when they hit each other, they should hit each other with enough force to cause the reaction to take place. So increasing the temperature increases the energy so they can hit each other and cause the reaction to happen. We can also increase the concentration, which kind of makes sense. If we want things to react, if we add more of them, then they're going to hit each other more often. So we can add more sugar and more water to cause the reaction to take place faster. And we're increasing the concentration of the reactants because we're trying to make the products. Okay. The third thing we can do is increase I'll do it this way, decrease particle size. Okay, so if it's not reacting and they're both solids, maybe we can grind them up into smaller pieces and they'll react more. Because when we grind up the reactants into smaller pieces, then we'll have more of them and then they maybe collide more often. So we can decrease the particle size. Another way that we can say this is increase the surface area. So when you make something smaller, you're actually exposing it more. So increasing the surface area may make it a little more likely that when they hit each other, they may be able to hit each other in the right spots. And then the last thing we can do is add a catalyst. And remember, a catalyst is something that speeds up the reaction because it lowers that activation energy. So it takes less energy or prep for the reaction to take place. One thing to keep in mind for catalysts are never destroyed during a reaction. They're just a way to help the reaction take place, so they themselves are never used up. Catalysts can be recycled over and over again, and catalysts do not change the reactants and they don't change the products. They just help you get to that point quicker. So they don't change anything, they just help change the activation energy, which is that in-between step. So you still start at the same spot, you still end at the same spot, but the activation energy is lower. So then that takes us to the last thing in chapter 18, which is Le Chatelier's principle. And this would be something that would definitely be on your exam and definitely on the test.